hope you had a good lunch. So I'm Anne, I'm a data scientist, and I work at adjoe. And today I'm going to talk to you about a very common challenge in mobile advertising. So it's called bid optimizations, and how we at adjoe solve this approach to this problem with our machine learning approach. So a little bit of icebreakers. I'm going to talk about myself first. I'm Anne. I'm a data scientist at adjoe. I'm doing my master's degree in machine learning and data science. And so far, I have 4 year experience in adtech. And another part of me is cats, because I freaking love them. I have 2 cats, and actually, I'm training one of my cats to replace me at my work one day. So. Okay, so back to where I work. So as Hassan said, we work at adjoe, and we are an ad tech company based in Hamburg, Germany. What we do, we make ad monetizations. So how many of you here have some mobile games installed in your phones? Raise your hands. Oh, that's great. So many support. So yeah, so it is quite common that when you play a game and then you finish a levels, usually there will be an ad showing up after you're done with that levels. So we are those people who determines which ads you will see in that moment. So to do that, we have our 2 main goals. So from the app user's perspective, we want to help them get the best user experience by showing them the ads that are interesting, or the games that they could they are interested in, new games, so they might like the game and install the games. And from the app publisher side, we help them to monetize. And how we do that, we will show the ads that helps them get the most revenues from. So how do we do that? We use machine learning. So we have different machine learning solutions that helps us solve these 2 main goals. So from the users, we use some machine learning models to match with our user interests and predict and shows relevant ads to them. And from the app publishers, we help we have some machine learning solutions that helps them identify the right users or high-value users, and then target the right apps for the user so that it helps them get the most revenue from these apps. Also, we are doing so we are working in large-scale systems. So it means that our data in-house has 600 terabyte of data to fuel our machine learning models, as well as some analytics purpose. And our machine learning models makes around 250 million predictions on daily basis. And because we are working in a very fast-paced environment, the machine learning models solutions have needs to be really fast. So currently, our solutions have less than 50 milliseconds latencies to adapt to these requirements. And of course, we are not stopping here. We are aim to scale more. So these numbers will change in the future. But we want to optimize our models as best as we can to adapt to our scaling requirements. And of course, we are not the only player in the market. So we are competing with more than 100 ad network in the compete with our 100 other ad providers, and many of them are big names like Google, Meta, or AdLoving. And where do we compete with them? In real-time auctions. So basically, in real-time auctions, we participate in the auctions, and the system will decide whose ads to show to those users. And the whole process, when you finish up levels and the ads showing up, it happens really fast, within 100 milliseconds, because it doesn't make sense to wait like 5 minutes to see an ad. So this is a really fast-paced environment. And so I'm going to explain a bit how everything works behind the scene. So whenever an ad publishers had an available ad space and they want to sell it, they will send the ad request to the real-time auctions, or sometimes we call it real-time bidding systems. And the real-time bidding systems will send the bid request to the players in the market, and whoever interested in participate will respond back with their own bids. So for example, here in these pictures, we are at network 1, and for this ad space, we think it's worth $5, so we bid with $5. And there are also other players like at network 2, 3, 4, and they also come up with their own bids. And because we are bidding the highest, so we won these auctions. But if you look a bit closer to these pictures, so at network 2, they are bidding with only $3, and we are bidding with $5. So what is the problem with that? Because what is the point of spending extra $2 if you can just spend 1 more cent and still being able to win these auctions? But there is a little problem to that. So we are not, because this is happening in 100 milliseconds, so it's really fast, as I mentioned before, and we don't know how much bids the other players will participate in these auctions. So we are applying to their own strategies, and we have to come up with our own algorithms and place our own bets. So it's like playing poker. So this could happen in a different scenario. So assuming that we want to be more conservative and we want to bid lower, like $3.01, and there is other ad network like ad network 2, and they decide to bid higher than us. So what is the outcome of this? We are losing these auctions, and of course we will ultimately lose the revenue opportunities as well as losing some potential users. So TLDR, for this whole problem, if we bid too high, we waste some unnecessary money. And if we bid too low, we risk of losing the auctions, and we lose the revenues and users' opportunities. And we don't know what the other players' strategy is. So we are blind to what the others bid. So what do we know? We have data. So we have the historical auction data that happened in the past. And from there, we think that maybe it makes sense to study some patterns in those past data. And we could maybe build a model that estimates our bids in real time. So that's why we come up with this bid price estimation model. And in our teams, we call it BPE. So this is the central idea of how BPE works. So there are two sides. The first part is the true values. So this is how much we think this as opportunities or this as impressions will worth. And this is estimated by our other models in our machine learning ecosystems. And there is also another side, which is the market values. So this is how much the other ad networks or the other players thinks this ads will worth. So if you look here, if we bid with the true values or even higher than that, we don't make any surplus or any profit at all. And if we bid lower than the market values, then we are losing these auctions. So the idea of BPE is try to find a bit in between these two values that helps us being able to win these auctions and at the same time save some money. So sometimes some literature refer these techniques as bit shading, but we call it BPE from here to be convenient. So this is the two main goals for BPE. On the first goal, we want to estimate the second highest bid in these auctions, and the second goal is try to find a balance between the true values and the actual bids, so that we can still be able to make some margin out of the auctions. So what are the options we have from easy to difficult? On the easy side, we could go with rule-based. So you could have your own strategies by countries or by user segment. You could bid higher or more aggressive for some part of our users, or you could bid like lower in some countries due to competitions. And on this difficult side, there's a method that are being used by some companies in the industries, and it's called reinforcement learning. So reinforcement learning, in short, is like we have an agent that learns how to bid through trials and error or explorations and exploitations. So this is actually indeed a very powerful method, but it is quite expensive in the initial phase because the agent, while trying to learn how to bid, it could make a lot of like bad decisions in the initial phase. So if you are the one who decide which methods to implement, which one would you go for? So who will go with the easy options? Raise your hands. Okay, and who will choose the difficult way? Okay, bold. That's bold. Oh, so indeed, we are going with neither of them because we want to have a balance between like the controls, and we want to have more stables, and we also want to have some performance. So that's why we choose somewhere in between, and that's why we use machine learning. So if you look at this problem in the machine learning perspective, we have some input data, and what we want is we try to predict the second highest bid for the auctions. So this is a regression problem. And what the regression problem does is try to find the lines of best fits of all of our data points, and it will try to, in our case, is predicts the mean winning bid for that auctions. And how does it do that? It's through some loss optimizations. So here is one example of the loss that we could use for regression problem. It's called root mean square error, or in some case, there are mean square error or mean absolute error. But the common thing for this loss is that it is the distance between the predicted values and the true values. So, but there is no weight multiplied to that. So it means that if the model under predicts or if it over predicts, it will have the same penalty. So imagine that if the model predicts $1 higher, or if it predicts $1 lower than the actual values, then it will get the same penalty. And it leads to a limitation to this approach because you are locked in 50-50 winning-losing strategies. So why we don't go with these strategies is, for example, for this user, how about if we want to bid more aggressive because we want to win this user and we want to win 80% of the time, or for some other users or some other auctions, we would like to win like just 20% chance. So this regression doesn't give us that flexibility to choose our bidding strategies. So this is why we go off. We chose another approach, and it's called quantile regressions. So quantile regressions, the idea is similar to regressions, but it also models the conditional quantiles of the target. So how does it do that? It uses the ping-pong loss. And how is this loss defined? So there are two parts. So the first part is the distance between the two targets and the predicted target. And the second part is the weight that it will multiply with. So if the model's underbid, it will be multiplied with q'd or quantized. And if it's overbid, it will be multiplied with 1 minus q'd. So you could see here that the loss is not symmetrical as regressions. And this is an example for that. So for a lower quantized, so for example, for this auction, we want to bid with, we want to win with a 20% chance. And what this ping-pong loss does is, if the model predicts lower, then it will be penalized by 0.2. And if it's predicts higher than the true values, then it will be penalized by 0.8. So it means that it will be penalized more heavily for over prediction case. And overall, it will help the models to learn that at this lower quantize, it should be slightly lower than the mean, so that it could have like a winning chance of 20%. And in the another scenario where we have a higher quantize, which is 0.9, and if you can see here, if the model bids too low, it will be penalized 9 times more than bidding too high. So here, the model learns that it should be bidding slightly higher to be able to have like 90% winning chance of these auctions. And this is how it looks visually. So in the first chart, we have here the line of the regression fit to our data points, and it cuts right through the middle of the data. So we see that half of the data is under the lines and half of the data is above the lines. But if we model this with quantile regressions, there are more, you could see like the distribution of our bit spectrums. So for example, the line red, which is targeting quantile 10%, is sitting lower than the higher quantiles, which is like yellow of quantize 80%. So here we could see that we could ask the models like how much I could bid to win and what kind of bidding strategies I would like to choose for these particular auctions. And so this is about how the overall structures of our full BP model. So it's still following the quantile regressions, but it has different layers. So in the bottom, which is the features that we use as input to our models, we have different type of features like user-based or contextual, temporal, historical auction data. And after that, we convert them into different representations. So for example, for numerical features, we convert them into dense inputs, and for categorical features, we could convert them to embeddings. And after that, after we have the vector representations of those features, we forward them into a special neural network structure. It's called gated deep cross network. So we had a very nice presentations about gated deep cross network from our company by our colleague Hafez. He's sitting in the front row last year. So if you are interested, please go to YouTube and watch his presentations. I learned a lot from it. But the main idea for this gated deep cross network is that it tries to learn the cross interactions between the features, and it also tries to identify which interactions are meaningful for the models so that it could learn the best from those interactions. And the output is basically a linear layer with different inputs, and each of those inputs will target to the quantize that we want to specify for these auctions. And yeah, after we have our model predictions, we have the quantize, and so we know how much we bid. But then we could go. We want to maximize the. We want to maximize our surplus, which is like finding the balance between the true values and the bid that we go with, as I mentioned before. So this is the expected surplus functions. And how is it defined? It's defined by the estimated value minus the bid that we chose and multiply with the probability of winning this auction given the bid. So the second part, the probability of winning this auction given the bid, is we assume that is equals to the quantize that we selected for our BP model in the previous slides. And so the main point of this process is to find the optimal bid that has the optimal win rate and maximize the surplus functions. How do we do that? Here is a simple pseudocode that we use. So the main idea is we initialize the optimal bit to be some values, for example, zeros, and the max surplus to be minus infinity. And then we loop through different quantize. We get the bit that associate with that, and then we plug it in back to our surplus functions. And if the and then we just try to do it iteratively until we find the surplus that has the maximum values. So there's also another related paper that I link in the end of the presentations. So after the theory, I'm gonna show you some example. So assuming that our different models, other models in our ecosystem estimate that the true values of this ad opportunities to be $5. And our BP models or quantile regressions predict different output for these impressions. So how do we read it? So for example, in the first quantize, which is 0.1, we bid with $1. So this means that we could have 10% of bidding higher than the other players in with this bid of $1. And for example, for the second quantize, which is 50%, we could bid with $1.8, which means like with this bid, we could be higher than 80% of other other players in the auctions. And then we plug the numbers back to our surplus functions. And then if you see here, the highest surplus is the second one, which is from quantize 0.5 when with bids $1.8. So it gives us the maximum surplus, and then we could use this to participate in our auctions. And we actually did an A/B test for our BV model, and the results, the initial results are quite good. So we have stable winning rate, same as our current baseline, and the bid is 12% lower. So it means that the model started to learn how to bid more efficiently, and we could actually start to have some margin from this new approach. And the next steps is trying to constantly improve our model. How do we do that? We could integrate new features into our models and make it more accurate. Or at the same time, we could try with other modeling approaches that are being used in the industries to actually update it with the curve and be more competitive in general. And yeah, so now you have some ideas what happens in those 100 milliseconds between finishing a game, levels, and using that. So here are my 3 conclusions. First, sometimes using the model prediction as is not optimal. In our case, we have some models that have us predicted the values of the ad impressions, and but the optimal action is not using it as is, but we could use it as a second layer of optimizations for our BPE model, so that we could both win the auction and as well as try to make the profit from it. And quantile regressions is a great tool when you care about the whole conditional distributions of the target given the inputs, so it's not only the average. And in our case, quantile regressions help us to select what kind of bidding strategies we could use to participate in the auctions, and we could go as conservative or as aggressive as we want, and it gives us that flexibility to do so. And my final conclusions is effective machine learning solutions are often multi-component systems. Why I say that? So this BP model is just like a small part of our whole machine learning ecosystems. So we have different other solutions that support these models. And usually to solve a business problem, we need not only one solution, but it's more like an orchestrated systems of different pipelines and different logics to work well together. And yeah, that's pretty much about my presentation. So I hope that you enjoy it and you have some more idea about how real-time bidding works. And here is a very nice engineer's blog from our company. There are a lot of like nice articles, and you could read about not only data science but also like infra, ad network, or anything related to adtech. So I hope you enjoy my presentation, and thank you for your listening.